All right, hello everybody. Welcome to another OWASP Toronto chapter meetup. We have another super exciting presentation for you guys today. But before I begin, a couple of housekeeping items. If you're looking to provide us with feedback or looking for CPE credits, there's a link in the description of this video. Please submit your name or your feedback there. Huge thanks to Tread Micro for offering us the space and the amenities. Yeah, huge thanks to them. And yeah, thanks to our sponsors as well. Guy, you ready? Floor is yours.
All right. Let me try using this. Hopefully you can hear me well. Welcome to my talk. It's going to be about the current state of the insecure deserialization vulnerabilities. I'm going to start off with who I am and what I do. So I actually work in these offices as a vulnerability researcher at Trend. What my team does is research end-day vulnerabilities, meaning they've already been disclosed, and what we do is sort of research the details, the root cause analysis of what the bugs were. We also provide detection guidance. That's the core value that we bring, is being able to detect these attacks over the network. Previously I worked as a penetration tester, security consultant, even before that a little bit as a programmer in C. Got my bachelor in computer engineering back in Israel, and OSCP, all kinds of fun certs. This is basically the overview of what we're going to talk about. So I'll start off just with a general description of what deserialization means. I'll give a simple example of what a deserialization gadget looks like. And then we'll dig into some vulnerabilities. So these are like recent vulnerabilities in high-profile products. So you get to see the latest in current research into this class of bugs. So first of all, let's start off with defining like what serialization and deserialization means. So if you're not familiar, a lot of programming languages these days, they use objects. So if you've heard of object-oriented programming, that's the way that a lot of state of an object is stored in the program. So it's a class, it has members, it has functions, but if you want to take that class and transmit it over or store it for later use, the easiest way to do that is using serialization. So it's basically a process of converting that object inside the program, turning it into a stream of bytes. So basically, it's something you can store somewhere, right? You can store it in a file, in a database, or even just in memory. And the process that happens, the backwards process, turning that stream of bytes, whatever format that is, into an object in the code, is the deserialization process. So to sum up, the deserialization is just taking a string of bytes, processing it, and turning it into an object inside our program. So what could be the issue here? Basically, it's if the stream of bytes that gets deserialized is untrusted, right? An attacker has some access to that data, is able to manipulate it. And if the application that's doing the deserialization isn't checking the object properly, isn't looking through the bytes, and a lot of the core issues are in type checking, so checking what types of objects are being deserialized. And we'll get into a lot of examples. So the really the flow that usually happens where insecure deserialization turns into remote code execution, which is the worst impact of this, is when you have basically a flow that reaches from the source, which is attacker-controlled input. And sometimes this can happen in two stages. One stage is the attacker changes the deserialized input, and the second is the actual deserialization process where it's triggered. And we'll see an example of that in one of the bugs. But basically, attacker controls the input, it triggers a deserialization, and then the process of getting to RCE is trying to get the deserialization process itself to trigger one of the interesting functions. So these are called sinks usually, and in Java it'll usually be running runtime exec, which runs a command on the operating system. In C# it'll be starting some process usually, but any interesting functionality that can get us to execute code. And a term that I really liked that was coined when this was just discovered, these kind of attacks, is property-oriented programming. So if you're familiar with return-oriented programming, it's kind of a similar concept where you're abusing existing code in the program and calling a bunch of properties, setting a bunch of properties, and then during the deserialization process, you're getting the code in the program to run in an interesting way where you control it. And we'll see an example soon, but this is just a call stack from one of the gadgets that's used in YSO Serial. It's an open source program that allows you to generate gadgets. So it's able to generate objects that once they're deserialized will get you remote code execution. And in this case, it's relying on Apache Commons. So that's a library very popular in Java applications. So because you see there, there's basically a little, let me just use this laser pointer. There's this class that's in Apache Commons that's being used, and that's why it's going to need that library to be included in the code that's used by the application to actually abuse this functionality. But this is the call stack that starts from the deserialization of a hash table in this case, and eventually leads to the sink that is runtime exec in this example. And this is just a list of some open source projects that generate these deserialization gadgets in various languages, and very useful tools for penetration testers. So yeah, I just wanted to give like a little example just to get a little more into the code and see it in real life, like how do these gadgets work. And I wanted to give a simple example. So I took one that's from the YSO Serial library. And this one is kind of special because it doesn't require any third-party libraries. So it's just relying on pure like Java code. The only caveat is that it doesn't result in remote code execution. What it does is trigger a DNS request. So it's actually a very valuable tool in penetration testing. So if you want to send some stream that you suspect is being deserialized and check if there's actually insecure deserialization, you can send this gadget, wait for the DNS request to return. And if you got that DNS request to trigger, you know that you've got a vulnerable function there. And this is basically the result of running YSO Serial with that gadget. I put like the URL to be OWASP, obviously. And you can see here actually in the payload some interesting stuff. So one thing to note, this is, by the way, Hexdump. So you can see it in hex, and on the right, the string format. So ACED is sort of the signature of Java serialized objects. And you can see here in the string version some of the class names. So Hashmap is the main object that's used, and inside the Hashmap we have a URL. So you can sort of figure out what's going on here, but this is all documented if you want to go into the weeds of the format. And yeah, this is sort of like just an example, simple Java application. It reads some data and then tries to deserialize it. And the data I gave it to decode is exactly that gadget that we just saw. Obviously, in real applications, instead of a hard-coded string, this will be something that's attacker-controlled. But yeah, this is basically just base 64 decoding this value and calling read object on the object input stream. So if you see this kind of code in Java applications, you should be suspecting there's some kind of issue related to deserialization there. So this is the call stack that you'll see from this code, and things to highlight are the read object called on the object input stream, and later the read object that's called on the Hashmap. That's the main object there. And eventually you see we reach the URL stream handler get host address, which is what actually causes the DNS query. And yeah, if we want to look through the code, this is actually code from the Java, the Java JRE itself. A hash map is basically just, a map of keys and values that can contain like any type of object. So in this case, we gave it a URL as a key, and once we deserialize it, right, this is the read object of Hashmap, we basically see that it's calling hash on that key. What happens if we call hash on that key? Well, this is just from a debugging session to show you, okay, we reached Hashmap read object and our key is a URL. So this is the URL there. And once we called hash on our URL, basically what's going to call is that object dot hashcode. So that means the URL object is going to be calling its hashcode function. So the URL's hashcode function calls its handler dot hashcode. Okay, let's dig a little deeper. And in our case, this is the URL handler. And you can see here very clearly, it's calling get host address on our URL. So that is where we wanted to reach. This is what's going to call that, make that DNS query. And even if you look through the Java docs for this class, you'll see it's getting the IP address of our host, and we'll make a DNS request. So yeah, before I move on, any questions generally about like this class and gadgets in general? All right. Okay, so I'll jump into some of the juicy stuff. So I'm going to talk here about some vulnerabilities in some top-end products. So SolarWinds was a bit in the news because of a hack they had, but they also, the reason it got a lot of attention is because their products are used in a lot of enterprise environments. And the Orion platform is the base platform that's used by a lot of their products. So an interesting place to look for bugs. So the first bug, oh, and by the way, each bug is going to have like a little meme associated with it. I thought I'd, connect to the youth better that way. And credit, by the way, for this meme to the Newington, I think that's how you pronounce the name. basically he wrote a nice blog post about this bug, but the actual discoverer of this is Piotr. He's from ZDI. So this bug was submitted through ZDI, which, fun fact, like just a week ago, ZDI held Pontoon like right here in this office. So yeah, there were some great like minds around here. So yeah, ZDI got this submission from actually a researcher in ZDI. So it's one of a unique case. And yeah, I'm gonna dig a little bit into the code for this to try to explain it. And a little thing to note is the library they're using for deserialization. First of all, this is code in C#, .NET, and they're using JSON.NET for the deserialization process. And this was patched just last year in March of 21. So yeah, actually, I want to just jump into like a little white paper that is right here that was written by Alvaro Munoz and Alexander Mirosh. Again, hope I'm not totally butchering the names, but these guys actually had a talk in Black Hat in 2017, which really exposed like a lot of these issues in .NET serialization. And the nice thing I like about the white paper that they published is actually that they have a lot of details about each library that can be used for deserialization in .NET and for JSON in general. But here's what they say about JSON.NET. So a very popular library for JSON. An important thing to note is that the default configuration is fine. It doesn't include type discriminators, which basically means adding the types of the objects into the actual serialized JSON stream. So by default, it's secure. However, a lot of times developers do configure it to enable type name handling, which we'll see in the code. And whenever it's not set to none, we know that there are some types included in there. And one other thing to note here is it does perform verification of the expected type. So that's going to be another hurdle that we're going to need to overcome if we want to take advantage of the deserialization process. And I'll show that as well. So let's just jump back in. So as we noted, it does verification of the expected type to deserialize. And type name handling allows to configure if we have type names inside the stream. And we'll also talk about serialization binders a bit. That's also a bit of a background we need before digging in. So it's recommended to use serialization binders if you include type name handling in your JSON stream. So it's sort of a solution that allows to look through every type while it's being deserialized, and you can basically override this function called bind to type. That's called every time you encounter a type in the process, and decide what to do. What do I want to bind it to? And a lot of programs use this to basically check the type and say, okay, if it's this type, I don't want to continue deserializing. This looks fishy. Or they can say, okay, only if it's one of these types, I want to continue deserialization. So it's sort of been used in the security perspective, but there's a nice note here from the Microsoft documentation itself that this shouldn't be used for security. And we're going to see a little bit in future vulnerabilities how it can be overcome. But yeah, let's dig a little bit into the code here. So this code is actually a little messy compared to other stuff we'll see, but there's a little bit of obfuscation. But basically what you need to see here is, okay, we're calling some test action. This is user input that we get into the application. And it's calling deserialized object with types. And it's giving this type of action context base. Okay, let's jump into that function. It's implemented here. And here we see exactly what we were talking about, the serialization settings with the type name handling, right? So we said with setting of none, it's secure, but any other value, we know we have types inside the stream. So there could be issues there. If we dig a little deeper in the from JSON function, we'll see it does basically two functions. One is called apply deserialization blacklist, and the other is the actual deserialization process. So what does apply blacklist? Well, obviously, it'll look through a list of denied types. So this is basically utilizing that serialization binder that I talked about. And it's looking through every type in the process and checks if it's one of these, it's going to stop the process and not continue deserializing. However, the process they're trying to do here is look for anything that's in known gadgets, like the Serial.net project, right? They know these can be used for getting remote code execution, so they're trying to block those. However, the problem with this method that gadgets are always discovered, right? This research continues to evolve, and into Serial.net, there have been added some new types that they forgot to add here. And these are just a few of them that were missed, I guess, or weren't updated. So, okay, we know they're using type names. So that's an insecure form of deserializing. We know that there are known gadgets that they're missing to block here. However, we still have one hurdle to overcome, which is the expected types. So it's only going to deserialize an object of type action context base. So we can't really send any of these objects, right? It's expecting an action context base. So what's the plan here? Basically, maybe you noticed this in the original meme. It's trying to embed something malicious inside something valid, right? So action context base is the valid object it's looking for. Inside, we're going to have our nested gadget. But how are we going to do that? We need to find a place where we can sort of inject that object. So, okay, let's look at action context base, see where we can sort of shove this, our gadget in here. So we see a member here that's of type macro context. Let's dig a little deeper. Macro context also has a member there that's a list of context base. Dig a bit deeper. Context base. Okay, here, if you're familiar with inheritance, you'll notice that it's an abstract class, meaning that it doesn't implement the functions itself, but any of these above classes are implementations of context base. So we can use any one of these. If we choose to look through Swiss entity context, it has a member of type property bag. And one more down the rabbit hole, we reach property bag, which inherits from a dictionary that maps strings to objects. Now we see something that's interesting. Okay, we can put an arbitrary object into this dictionary. That's exactly what we wanted. And this is what the full payload looks like. I did truncate a bit of the beginning and ending, but you can see here the important parts, which are, okay, we have our alerting action context. It inherits from the context action base. And inside we said macro context, we have a macro context. Inside we have a Swiss entity context property bag. And right inside that dictionary, we put our gadget, which is of type session security token, but I could have used any of the missing gadgets from the blacklist there. So yeah, it's sort of using an allowed type and providing a malicious one inside one of the member properties there. So just to summarize what we learned about this from this one, blocking a list of disallowed types is not sufficient because it needs to be constantly updated, and you also don't know of like gadgets that aren't publicly known that attackers can exploit and keep to themselves. And second thing, relying on the checks for expected types, that as is done in JSON.NET, isn't sufficient because even though we're sending a valid object, it can contain malicious inner properties inside. Any questions on this one before I move on? Another meme then. Yeah, so we're going to get, I guess we're going to get a little more recursive here from the meme. And this one was actually discovered by the same one who wrote the blog about the previous one. So I guess once you dig deep, you find bugs yourself. As is done in a lot of end-day research, you can stumble upon a new 0-day, as was the case here. And this one was patched July of last year. Of course, yeah, again, submitted through ZDI. So, okay, let's start from the source here. So our source in this case is Orion render control. It's some kind of function that's processing a post request, an HTTP post request, where the body can contain some JSON data. Okay, looks innocuous so far. We're loading the JSON data. This is the load JSON data function, and we're just reading the attacker controlled data and calling deserialize. So this looks pretty bad, right? Like we're just entering input into deserialize. But notice the formatter here is JavaScript serializer. We haven't seen that one yet. So let's look up our trusty guide if I can close this thing. Okay. Let's look at the JavaScript serializer. So by default, it doesn't include type discriminators. So you need to actually supply a type resolver for it to be in a non-secure configuration. And here we just see a simple use of it. There's no type discriminator provided. So this is actually secure deserialization. This is how it's done right. But yeah, anyways, it would be too easy if it were just this one function, right? So let's continue on. We read the JSON data securely. Now we're getting some parameter called control. We're loading it, and then we're calling this function that applies properties and attributes on the control. Okay, so far all we could control is this control parameter. Okay. What can we do here? Okay, first of all, load control, what does it do? It simply accepts some kind of path to a control and loads it. What happens here, where it's applying the properties, is the more interesting part, where it's basically reading the data that we fetched from the JSON data. It's basically right here, trying to get values from the JSON data. It's called fetch in the output. And this data is sent into set properties with the control that we provided. Okay, we're sending a list of properties. We're sending it to set properties. Again, it's just iterating over the properties, calling set. And here, what we see is what's called .NET reflection. So this is where we're able to, from the type of an object, be able to get all the properties of the object and set them. So this is really like low-level .NET stuff here. And as you can see, this function basically allows us to set any property we provide, right? We're in control here of the name and the value. So this is quite strong functionality that can be abused. And we'll soon see how. But okay, so far what we saw is we're able to call an arbitrary setter function. So a setter is basically any function that sets a property of a class. And in this case, that class is of type template control. So, okay, we can set any property of this one class with any value. How do we get like remote code execution? So if you dig enough into the code here, you find this nice class called action plugin base view. And if you look through the hierarchy, you'll see that eventually it inherits from this template control. So it's a type that we're allowed to send to control here. And okay, usually setter functions, they simply, getter or setter functions, they get or set a property. That's all they do. But sometimes there's some added functionality. And in this case, with this property called view context JSON string, we see that the setter function, it does set the value to whatever we provided, but it also calls this extra function at the end, parse view context. What does that do? Now we get to the juicy stuff. Now we get to JSON serializer settings that's using type name handlers. So just as we saw before, we're using the JSON.NET library to deserialize an object. And we're doing that, in this case, on one of two types, either alerting action context or reporting action context. But again, we're seeing this is even worse than the example we saw before, because here there's not even a blacklist of types. We're simply deserializing the object. And this is a parameter that we control, right? We can set this parameter with our setter. And the nice thing about these two classes is that they both inherit from action context base. If you remember, that's exactly the class that we used in the previous vulnerability to exploit the past vulnerability. The same gadget chain, we can just reuse it. So very useful stuff. So the overall idea here, okay, we're going to send a JSON object to the vulnerable endpoint. We're going to need to set a control parameter that inherits from this interesting control that we saw. We need to set a config parameter, which, it chooses to set this parameter with our crafted JSON. And that crafted JSON can represent either of these two types. And after that, that setter is called, we basically get the insecure deserialization to trigger, just as before. So you'll see it does look quite similar to the previous payload, right? We see this alerting action context, macro context, Swiss entity, property bag, this whole gadget chain. It's just now embedded into a parameter of this control. So very similar functionality, basically reusing the same gadget that we used last time, and in an interesting way. So the one lesson I think we learned from this one is basically calling an arbitrary property setter. So being able to set any property of even a specific class is dangerous functionality that we don't want to open up to attackers. Any questions on this one? All right. So yeah, let's move on to another very popular product. It's been in the news quite a bit with all the funny names of vulnerabilities it got. Proxy logon, proxy shell. Actually, the last vulnerability I'll show here was called proxy not shell, because yeah, they're really not original with the naming. But yeah, I'm going to cover a few of the vulnerabilities in Exchange, and we're going to see that they're all very related. So the code paths are all very similar, which shows you how digging into a specific vulnerability can really teach you a lot about other similar vulnerabilities that may exist in the same region. One thing that's common to all these vulnerabilities is they all use the binary formatter. So actually, this is like known to be insecure since 2012. Actually, James Forshaw gave a talk at Black Hat. He demonstrated how this can be abused, this formatter. But only in 2017, I believe, the Serial.net project came out and really showed gadgets that can be abused to get RCE using this formatter. So that's when the attention really got out that, okay, this is something serious we need to fix. And this is from the Microsoft documentation. I really find it funny that like they're saying very clearly in their documentation, like this type is dangerous, not recommended. Stop using this, like not even like with trustworthy data, right? Like don't do it. And yet like this is used again and again in their Exchange product, like one of their big products. So, you know, it's hard to follow what you preach, but to their credit, they are working really hard to use it in a secure way, and we'll see how. So yeah, first one is 42321. Doesn't have, I think, a fancy name to it, but this one was patched in November 21. And as I referenced, it's using the binary formatter. And like the first example we saw, it also uses a serialization binder, which checks every type that's encountered in the process. This is just the name of their binder. And yeah, discovered by a bunch of people. Yeah, okay, so this is where the vulnerability lies in a typed binary formatter class. Not really sure. When I was looking through this, like I wasn't sure what's the context in which it will be used, but we'll get to that later. Let's first look at the bug itself. So, okay, we're calling, if we call Deserialize with this class, we're calling a function that creates our binary formatter and then just calling Deserialize on it. One thing to note is that the second parameter there is set to false. That second parameter is what they call strict mode. And this is just sent into their binder. So they basically implemented their own serialization binder, looks through every type that's being deserialized, and they decided, okay, we want the flag to decide how strict we're going to be about it. So let's see how that went. So this is the binder itself, and this is the function that is used to deserialize. So sorry, to bind the type. So this is the custom function every serialization binder needs to implement when it's going through the types. It gets the type that's being deserialized, and it runs whatever functionality it wants, but at the end it needs to return a specific type. It can also obviously throw exceptions, which will cause the deserialization to stop. So what do they do in this case? They bind the type, and then they call this validate type to deserialize. Okay, this sounds like the place to look. A little bit of a mess here, their code, but to summarize what's happening here is if the strict mode is set to false, which it is in our example, the first check just checks if it's inside the type that's being deserialized is inside this list of global disallowed types. Okay, so that seems very similar to the first vulnerability we saw. Basically a list of disallowed types that they don't want to continue deserializing. And the rest of the checks here, I didn't include it because it's too long, but basically checks allowed and disallowed types, but in case of an exception, it just throws a blocked deserialized type exception, which doesn't get very far. It's caught right here. And the problem is that if the strict flag is set to false, which it is for our case, it isn't thrown. So all we'll get in the case of the other checks here is just, it's going to be logged here in some place, but it's going to continue deserializing. So to summarize, all this does in strict mode is set to false is check the global deserialized types. This is a list of disallowed types. And if you're familiar enough with .NET and these gadgets, you'll notice that there's a little typo in this one. So they wanted to write system security claims principle, but forgot the claims. And yeah, that sort of was a big typo that could be abused. The problem is that during the discovery of this vulnerability, there actually wasn't a gadget using claims principle, but there was one that used claims identity. So the discoverer of the vulnerability figured, okay, they're blocking this claims principle. Maybe I should look into that one. And apparently it's a very similar gadget to claims identity. I mean, the names are very close as well, but it's actually a very simple gadget. I can show like the flow here. It's basically has, when it's deserialized, it just calls this Deserialized Identities function with a member of its, that, when we're deserializing, we can control this member. And this Deserialized Entities, all it does is decode the base 64 string inside here and just call the binary formatter without any protection whatsoever. So any gadget can be thrown in here inside these identities. So very simple gadget to abuse, and it was added to the WISO serial project as well. So anyone can continue using this gadget. Okay, so yeah, as I mentioned, like the path to this vulnerable code was where I was stuck actually researching this, and I was like, how do we actually get to this function? Apparently, the answer is it's complicated. Like this is actually just half of the stack trace to get there. And it has to jump through some like interfaces. Like you really have to dig through the code and work your way up from that call. And you'll eventually reach this function called get client access token, which that is actually an API that's a SOAP API provided by Exchange. So that's basically the source triggering all of this deserialization. And inside of that, long stack trace, you should have seen, okay, there's a call to try deserialize, which this is where you actually control the data to be deserialized. It's getting the data from a user configuration. What's a user configuration? Okay, this is actually another there's actually another SOAP API that allows you to set an arbitrary value for a user configuration. It looks something like this. You basically set a called create user configuration. And the really nice thing about this API is that it allows you to set arbitrary data into this object. So it has a feature like where you can set binary data, and you just provide some base 64 string. It'll decode it and set that as the value of that object. So very useful for exploiting this one. And yeah, like all of the exploitation looks like here is creating a malicious configuration. And here we'll put our payload, for example, the claims principal one that we saw. And then you call get client access token, which triggers the actual deserialization. So, as I mentioned in the beginning, it's a two-step process in here. You set the malicious data, and then you trigger the deserialization. So to summarize from this one, we called this custom serialization binder with strict mode set to false, which was the big issue here, which only checks disallowed types. And this list of disallowed types, as usually you'll see, has some kind of flaw in it. In this case, there was a typo in one of the types. Questions on this one? All right. Another meme, another CVE, something to do with strictness. Okay. Okay, so this one was actually had a nice blog post as well by Code White. It was patched just January of this year. And you'll see that you basically, if you read the blog, you see that he was inspired by the blog that was posted about this like last issue we just covered. So, when researchers post this kind of data, like it really helps dig deeper into these issues. And you'll see it's a very similar type of issue. So it still has to do with the binary formatter and the binding process. So this is the call path. I just thought I'd start off with like, okay, this is how you reach the vulnerable function here. It's an RPC call that allows you to import a certificate. But yeah, basically, this is where the interesting stuff happens. And this should be quite familiar, right? Like we're, again, getting some strict mode. We're using that value to create a binary formatter and then deserializing. So far looks pretty similar. However, before the strict mode was set like just to false. What do we do here? We're getting the strict mode status from some function. Okay. And yeah, again, the create binary formatter hasn't changed. It's exact same code. So when we're getting the strict mode, this is also looks like a whole lot of functionality for a simple thing, but basically all it's doing is looking up in the settings for the deserialization binder and checking a bunch of values, but based on the location where it's used. So that's the key point is what's the location. And I think in this case, this was the location, exchange certificate RPC. Okay, so basically it's checking if it's in the disabled locations, in the learning locations, and if it's in the enable locations. So this is what the settings look like for the binder. It's just in an INI file. And, okay, strict mode is enabled. There's no disabled or learning locations. But the enabled locations don't include our location. Okay, after all that, functionality, we figured out, okay, our specific location has strict mode set to false. So again, we're using the binder with strict mode set to false. But, obviously, Microsoft has patched the typo. So we need to figure out a new gadget that we can abuse. luckily, the same researcher that was looking into this posted a tweet about a year before about a gadget that they wanted, some kind of gadget in .NET that's similar to the one that we covered in the beginning, the one that triggers a DNS query. So that one was in Java. He's looking for something similar in .NET. And he actually found one that has some, added functionality. So this directory info class, when you deserialize it and call it, and its constructor is called, you can basically trigger an NTLM hash being sent to, an arbitrary location. So this is really useful for NTLM relay attacks, right? So if an attacker can set this, create this class and set this to a server that they control, assuming that SMB signing is disabled on the host, they'll receive the NTLM hash and be able to use that to relay it to further devices. And yeah, this is like from the documentation itself of directory info. It says that it supports UNC shares. So that's just part of the functionality of this class. But I guess they didn't think it would be used as a deserialization gadget. So yeah, that's how they got, like, basically to prove that you can get RCE using this this chain. So we very similar to the past one. Okay, we had strict mode set to false. So they haven't closed down all the code paths for that. And getting a list of disallowed types isn't sufficient to block all vectors. There's always new and creative ways to abuse these new gadgets. All right. I think this is second to last one I wanted to cover. So here we have something. Okay, we're digging into the core, probably .NET Core. Okay, so again, research by Code White. This one was patched in March of this year, so fairly recent. And the vulnerability here is actually in the binder itself, so it's not even in the usage of the serialization binder. That's why, we're going to need to dig a little deeper into this one. So, okay, this is just to show that they've fixed the way they're getting the strict mode. So they're not checking allowed locations anymore. They're by default allowing all locations to be use the strict mode. So that's a good change. And the settings have also changed. There is some, comment here. Some places aren't using this functionality, but it shouldn't be used in, I guess, in their regular code paths. So yeah, strict mode seems to be enabled in all the code paths that are relevant for us. So how can we still bypass the binder? I mean, we're not relying here on some list of disallowed objects. We need to find some other method of bypassing this binder. So, okay, let's look again at this binder. This is the bind to type function that we saw before. And we looked before mostly at the validate type portion. Now we actually want to look deeper into the actual type resolution here that's being done. So this is the call to internal bind to type and then load type. So how is it resolving a type that it's encountering? And yeah, this is what the binder does. It tries to get the type by taking the type name and assembly name. And it's also trying to take all the loaded assemblies and, just try to load the type using each one of those assemblies. But what does this actually mean? Like assembly name, type name, like let's try to understand this a little bit better. I won't go into like deep details, but this is really like nice stuff, and we do need to encounter this sometimes in our research, is looking through open specifications by Microsoft. So, the binary formatter, just like the JSON format has a clear specification, the binary formatter uses its own format, which is called the .NET remoting binary format. So, these structures have to be defined, and that's how these programs can deserialize and serialize the data and understand what's going on. So, the way that the binary format includes the class type is in here in the type name. And you'll see that it's referencing that the type name needs to be of a format that's actually specified in another open specification. And same thing for the binary library. So that's how it's getting basically the assembly name. And again, it's telling us the library name is also specified in that other specification. Which one? It's this one, the .NET Remoting Core protocol. And that's like, okay, this is the basic definition of .NET remoting. And this is how they describe what does a type name look like. And this is where they define what does an assembly name look like, or a library name. And one more thing that we need to understand is like there's something called an assembly qualified name. It's basically when you take the type name and then add a comma and put the assembly name. So this is like basically the full name of a specific type, a way to clearly define it so there's no confusion. Why do we need to know all this? So we'll get to that in a second, but the binary formatter, okay, when it actually does the deserialization, you'll see that it eventually reaches this function that we'll see in a second called object reader bind. And this is where the magic happens. This is where the bind to type function that we saw for the serialization binder is called. So we want to look deep here into the functionality that's happening when we're calling our binder. So, okay, so one thing to note is this case, the if type equals null. So if our custom serialization binder returns null, what will be called is this this function fast bind to type. Okay, this looks like a last ditch attempt to sort of like resolve the type somehow. What does it do? It gets the assembly name, resolves it, and then it calls this last function get simply named type. And eventually, I cut some stuff out, but it'll eventually call get type with our type name. And the nice thing that the researcher discovered about this specific code path is they tried submitting a type name here that is the assembly qualified name. So basically, this full assembly qualified name, they put in, the program is expecting just this first part, the type name, but they're submitting in the full name, including the assembly. They found that this function actually resolves that type. So, you can it's sort of a nice little trick to give a type name that doesn't seem quite valid. It shouldn't be including the assembly name, but it seems to be resolving using this last ditch method. So how can we bypass? Our general idea here is to specify a type that's going to include the assembly name, a type name including assembly name, and then the assembly we can set to anything valid. What's going to happen here is, the internal bind to type, that's our custom serialization binder's attempt to find out the type, it's gonna fail and it's gonna return null because it wasn't able to resolve the type. And as a consequence, we're actually gonna completely skip all validation done by the serialization binder, because this only enters if the type isn't null. So we basically, okay, we haven't resolved the type, we skipped validation, so we'll still return null here. But what happens when we return null? We looked at this. The type is null, we're gonna call fast bind to type. And as we just saw, this last ditch attempt to resolve the type does resolve it properly with our custom type format. So basically, we're able to resolve any type we want and completely skip the serialization binder. So this is a really cool method. I'm sure there are other serialization binders that are vulnerable to this issue. They actually, in the blog, they did mention another product that's also vulnerable using that same method. But what I like here is we're really like abusing the core functionality of the serialization binder and relying on the fact that some cases this bind to type function will return null. So yeah, that's what like I learned from this one is, okay, if I'm looking at code where the bind to type function implemented by this custom serialization binder returns null, there's a way to still get it to return null and resolve a type. And this will allow us to bypass a lot of binders. Any questions about this one? All right. Last one. This one, yeah, it was very recent. This is the one, yeah, I think was dubbed Proxy, not shell, but yeah, bad names. This one also was submitted through ZDI. And yeah, I'm not going to try to pronounce whoever discovered this, but yeah, it was patched just last month, so very recent. And in this case, a vulnerable class is this exchange binary formatter factory, which I believe we've seen quite a few times. So just a short thing that we need to understand beforehand is Exchange has this nice functionality allowing you to control some of its, get mailboxes, all this like sort of management, and do it through PowerShell remoting basically. And it's all done in this nice management shell product. So very useful feature, but apparently can be abused. So, okay, what's PowerShell remoting? I'm not going to get into the specification, but this is just a simple example, like from the specification itself. It allows to define type objects with their own types and values and properties. Like it's quite a rich specification. So this is the functionality that's called when a PowerShell remoting object is read by the application, by Exchange. So this is the the stream that we can control, and it's reading an object. So this is an example of an object that's being sent. It's reading an object and it's trying to get the target type for deserialization. Now, this is always, interesting stuff because as we've seen a lot of times, controlling the type that's going to be deserialized is going to be very valuable for an attacker. So can we actually control this type? That's a good question. Exchange and PowerShell remoting in general allows you to define specific types that are allowed to be accepted by PowerShell, and it also allows to define what's called type converters. So these are called whenever you want to convert specific types. So you can specify your own custom type converter. And this will be used. This is where we're actually going to see, the deserialization process. So let's look into this type converter. So when it's calling deserialize, again, this looks very familiar to us, right? We're getting the strict mode status. We're creating a binary formatter and deserializing. We've seen this over and over in the code of Exchange. In this case, though, we saw that due to previous patches, the strict mode is set to false by default. Set to true by default. So it's going to be strict, right? So what we haven't looked, though, in the past is at the allowed types. So, okay, we're going to have to use strict mode. We're only going to allow the specific types that are allowed in this list, the specific list for the serialization type converter. And yeah, again, like the create binary formatter hasn't changed. So the allowed types for this specific converter are, much longer than this list. I just put sort of the end of the list because there's some interesting type that's allowed here, which is called System Unity Serialization Holder. Now, what is that? Well, if we go back to the specifications for the .NET Remoting Core protocol, we'll see that this actually is assignable to system type. Interesting. So it's able to deserialize a type that is of type system.type. It's confusing to say this over and over, but yeah, basically we can control an object of type. So this is like a very useful object. How can we abuse this? Well, we can after we deserialize an object of type, we can use that, right? We got that target type for deserialization. Let's assume we can control that. We're calling convert to with that type. So we're able to convert to any type that we want. And if we dig enough into the code, we'll see that eventually it's going to try to convert using what's called the parse conversion. What is the parse conversion? It basically takes the type you want to convert to and calls the parse method on it. So I guess that's a way a lot of types are converted normally. But this is a pretty strong method that we can call. We can basically call the parse method of any type we want, and we can supply also the content, the parameters sent to that parse function. So this is actually a specific path that was abused in the past. I think it's called the PS object. That's the name of the gadget used in whysoserial.net that abused the same method of attack. And what it did was use an object called XAML reader. So basically, if you look at the payload that's been published in the blog, you'll see that it's setting a target type for deserialization that has a type of exception. The reason it's a type of exception, it's because the converter there is using our vulnerable serialization. So serialization type converter. So the serialization data there is set to our type that actually deserializes into a type. And the type that will be deserialized is a type of XAML reader. Okay, so this is what the crafted object looks like when it's deserialized, and it's going to eventually return the XAML reader type. And as we saw in the figure parse conversion function, it'll call the parse function of this XAML reader. And the nice thing about this function, the XAML reader, is that you can give it some XML data that will eventually lead to code execution. It's a really popular gadget in Serial.net. You can see XAML reader quite a bunch there because it's such a powerful class. And in here, like, in this example, they use the object data provider, which is another gadget, again, one of the, I think, first ones that was uploaded. So very simple gadget, relatively speaking, and it's basically called by the XAML reader parse function. And this is sort of like what the full payload looks like. Again, I had to, crop some stuff out, and it's still, well, actually here, yeah, I don't think I truncated. That's why it looks so small. But, if you can tell, like, this is setting target type for deserialization to an exception type. This whole blob of serialization data is basically a type of type, which is going to resolve to a type of XAML reader. And once the conversion is done, the XAML reader parse function will be called on this payload. So that's what we saw in the previous slide, which can get us remote code execution. So to summarize, okay, what did we learn from this one? We learned that we don't want to allow our attackers to deserialize an arbitrary type of type. So because they'll be able to basically create a type with that controls some interesting functionality probably. And in this case, this type was used for a conversion process. And because this conversion process used the parse method as well, we can call parse for an arbitrary type with attacker control data, which is what we needed to get our deserialization. And I don't know, like Adam asked me if there's some kind of like thing to demonstrate. I mean, I find most of these deserialization vulnerabilities kind of like underwhelming, like to show, but I did open up so the ZDI blog about this last vulnerability did include a little demo. So, if you're interested, what happens here.
Welcome to a ZDI exploit demonstration overview.
Python script.
This video shows a remote code execution bug on Microsoft Exchange server.
Be able to see it eventually. Okay. Yeah, so there should be like a little Python script in the top right. It gets the user credentials needed, and it calls, a command prompt that prints "Who am I?" And it just, obviously it's going to run as system, which is, very high level to be running your Exchange servers. But yeah, kind of underwhelming, but you get remote code execution as system using any user. So very powerful stuff at the end of the day. Yeah, so I just wanted to end with like few keynotes of like lessons I think I learned from like looking at these various vulnerabilities. One is, if you have an option of doing it, like don't deserialize at all. Like just use some JSON parser, use some secure method of like reading information into your application. If you do need to use deserialization, do it with secure and safe formatters. So, don't use the binary formatter like Exchange does. Use some better methods. And if you're using them, also make sure you're using them with the secure configurations. Just like we saw in JSONnet, you don't want to have those types inside the deserialized in the serialized stream. And last thing, the list of disallowed types, like I keep seeing it over and over again in applications, and it's really hard to manage and close down every single type that's, malicious. So just use an allow list. You need to know what types you're deserializing, and check that you're only deserializing those types. And yeah, I included hopefully this will be shared on the site, and you'll be able to read through the write-ups. Every single CV I covered here has quite an extensive write-up on it, sometimes even more details than I showed. So yeah, feel free to dig even deeper. And I included also that white paper that I opened up before. So yeah, thanks for coming over, and yeah.
Any questions for Guy? There's none on YouTube, but I guess while I think about it, have you used the chat GPT at all in your search for serialization issues?
Yeah, I mean, I've played around with the chat thing, but yeah, I have, played around to the extent of like sending it some code and asking it to find, like, can you find the vulnerability here? And it actually did find. So like, I'm quite surprised by like the potential that this has. I also have seen examples of people just sending it like blobs of like decompiled code from like IDA or whatnot, and telling it like, okay, describe to me like what does this code do, which is also very useful in my type of work, because if you're looking through this code, it's really hard to read sometimes and understand what's going on. So yeah, I definitely see this type of AI stuff entering into like the tools that I'm using, and like just aiding like in research. So a lot of potential for sure. Yeah. Any other random questions about AI or whatnot? Oh, okay.
Oh, I have a question.
Yeah, sure.
Do you have a pizza free now?
I think you probably have the answer to
that.
Oh, awesome. Okay, yeah, pizza has been provided. Yeah. So thank you everybody for coming out to another great presentation. Stay on the lookout for our announcement